And in cross-section, you see the regular layer here of photoreceptors. You see these globes? This can be seen because the transversal resolution is there for us to be able to separate laterally. Without adaptive optics in the OCT, we couldn't have seen this separation. So with the adaptive optics, you improve the transversal resolution. But what happens in reality is that's the as I have shown you an image from the eye. As you improve the adaptive optics, practically you reduce the confocal gate squeeze. You see here, this becomes narrower and narrower. So now we have to shift it axially, like with the Gabor filtering. And I'm showing there the focus profiles which you have to shift in depth to scan it well. So I've been through visibility decay. I mentioned the dynamic focus, and there is another one which is called mirror tabs. So what is mirror tabs? Everyone touching an OCT system based with a spectrometer based or a tuning laser will have this problem. So you look at the patient, that's the scan there, and if the patient moved closer to the system, now what you see an image being flipped and superposed on the original. Because points equally distanted from optical power difference will contribute to the same modulation. The same number of peaks in the modulation. So the interferometer, the spectrometer is blind, couldn't tell you if those 10 peaks in the modulation comes from positive optical path difference or negative optical path difference. They are superposed. And we call that the problem of mirror tabs. And we produce many papers on this phenomenon. It's called Talbot bands, a modality to eliminate the mirror tabs. And because I ran out of time and I presented that last year, that's an interesting effect. Let me go quick here. This is the lens in front of the camera. This is a diffraction grating, and this is a beam coming here to the diffraction grating here. So what I'm going to do, I'm going to place a glass plate in the beam, and when I put the glass plate into the beam, I will practically improvise a two-beam interferometer, because I will leave half of the beam going through air and half of the beam being intercepted by the glass. So that means that in between the two halves of the beam, I will have one through the air going quicker than the other one through the glass being delayed. So it's like I will improvise a two-beam interferometer. And look here what happens. So I introduce the glass plate and look at the spectrum. You see that Gaussian spectrum? The modulation. So anytime the edge intersects the beam, I should obtain that modulation. However, I don't obtain it all the time. So look here. It happens, but it doesn't happen when I intersect this with the beam. Watch that again. So you see, I went through and there was no modulation. There is modulation only when I intersect this one. So what's going on? It's the same beam, it's the same spectrometer, it's the same patient, the same manipulator. But it's like there is a difference between the left and right hand side of the beam. So when the beam is intersected here, we have the modulation. When it's intersected on the other side, so more here. If I put it this way, I may get the modulation. If I put it this way, I don't get it. So it's like we have a difference between left and right. It's good food for thought. It was discovered by Talbot in 1836, and Airy explained it 1 year later. So there's nothing magic. Simple interference of light. But we put put a lot of work into exploiting this interesting phenomenon for eliminating the mirror theft, because these Talbot bands, they recognize a difference, an asymmetry arrangement in between left and right. And this is exactly what you need to distinguish between positive and negative optical phase difference terms. And that's a system for Talbot bands. And if you do non-Talbot bands, like any conventional velocity in the world, you will have this curve. So if your tissue is here, creating a modulation corresponding to 1 millimeter OPD, it will be the same modulation at -1 millimeter. There's no way to distinguish between them. While with Talbot bands, you have this curve or this curve, i.e. Practically all this length here in between 3 - 3 is moved to the right or moved to the left. So there are no mirror taps here, while there are mirror taps with the old method. Okay, so polarization, what can you do with polarization? 2 channels, one sensitive to vertical, one sensitive to horizontal. You combine them in 2 interferometers. You look at the intensity of those 2. You do the ratio of horizontal and vertical, and you obtain an insensitive, polarization insensitive image, and birefringes. So what is the birefringes? The birefringes is quantification of rotation of linear polarization as the wave propagates of the tissue. So the retinal nerve fiber layer is birefringent. So if you see here, this whiter shades here in the birefringes image, which you don't see it in the intensity image, but the birefringes image will show. So if you do an average here from the limits of the retinal nerve fiber layer, you find this slope. This slope will tell you that for a thickness of 100 microns, the polarization will be rotated by 30 degrees. So you can do this measurement quick in the eye. And in the cornea, look at 2 images from the cornea, from the extreme lateral part. You don't see too much difference between H and V. If you combine them, you get the polarization insensitive, but when you produce the birefringes, look how exquisitely different this is. It shows you the junction between the cornea and sclera. Here. See? The junction here, which we barely could identify. The birefringes image will show. That is due to the collagenous links in the sclera. More about producing more channels by multiplexing, and again polarization. Mantas Urauskas obtained his PhD in ERC grant, and he looked at this multiplexer, delivering polarization sensitive imaging, and if you hit the tissue, you destroy the collagenous links, and I should stop soon. And what is displayed here is the intensity image, and this is the birefringent image. So if the tissue is heated up, you see the birefringent image immediately shows that the collagenous links disappear. There's no periodicity, changing the phase from 0 to pi and so on. Okay? So that's good for looking at burns. So I'm over the time. So I wanted to show you only the last slides with recommendations. So if you wanted to know more about OCT, you can go to these sources. There is a statistics of the fields being dealt with by OCT, and that shows where OCT has been used. In Kent, we addressed all this, and now we are working with Imperial College on robotics. subscribe and receive daily excerpts from Eric Swanson, one of the inventors of OCT at MIT. And that's our group. And if you go to our webpage, if you go to Kent and write applied optics, you should see here results. And there is a publication list which is pretty much updated with at least every 1 month. And there you can have links to open access publications simply by looking at our publication list, and that's the web page of the subcenter. I'll be around, so I run out of time, so I cannot give you time for questions. But if you wanted to stay longer, I can listen. So it's technology with applications. Depending on what you are interested in. Yeah, you can find these examples on our webpage. You can write it.
I think we can